problem sheet should be given by around 17 or 18, because we started like 24th, right? So we promised like a monthly one, so we'll plan to give it around 18 February. Yeah, next week, basically sometime in the next week we'll get it. And the practice problem you no need to submit, only assignment you submit. Yeah. Okay, so let's start.
Recording in progress.
So we started problems around partitions. Just recall from the last class. Are you getting a lot of noise from my end, or is it clear?
Now it's clear.
Okay. So we introduced about this Starling number of the second. Actually, did I write it first kind? It should be, I think, second kind. Yeah, this is. I think this was mistake. So this is second kind. Just a name, basically. There is something called first kind also, but that we are not doing at the moment. So anyway, it's just a name, SNK. So remember that what SNK was. There are n numbers, 1 to n, and you want to distribute them in the k identical boxes, right? We discussed some basic stuff, and then we wrote a recurrence. This was the recurrence that we explained last time. Okay, so we continue from that, and let's change the situation a little bit. Now make it distinct balls, and let's say n balls, and always identify them with 1 to n, and distinct boxes. Let's identify them 1 to k. So this is the problem, right? So you have n distinct ball and n distinct boxes, and how many ways you can arrange them in these boxes. That means, okay, let me just alert you that maybe some of you already know these stuffs, but some of you may not know. It is not expected that just after passing out of 10+2 you will know this thing. Maybe some of you have trained in some other camps or IITs or something like that. So people who have not seen it, feel free. We also have learned it for the first time. There is no need to be panicked by people who already may know it. So we'll all learn it from the beginning. So that's not a problem. Okay, so let me draw the picture. So this is your 1 to n. Let's say these are the balls, and these are the boxes. 1 to k. Now, so mathematically, what does it say? Like I have stated it in terms of balls and the boxes. And condition is that you have to arrange these n balls into k boxes such that nothing is empty, no box is empty, right? So does it remind you some more concrete thing in mathematics rather this ball box kind of analogy?
Sir, a number of surjective functions.
Exactly. So this is this ball, balls and box, this distinct feature reminds us this is nothing but counting number of. Particularly, I would recommend that people who have seen this for the first time, you should try to participate and get involved in the discussion. Then you learn it better. And if you know the answer of something from your earlier experience, you just allow others to understand and internalize it. Counting number of subjective, because we are slowly building the subject. We are still 3 months ahead. Counting number of subjective maps.
A small doubt.
Yes.
the previous, the Sterling number which we were talking about at the end of the last class, that is not for this counting, right? That is for n.
No, that is like, yes, that is, boxes are indistinguishable there.
Okay.
Now I just tweaked the problem, but you can immediately probably see a relation between that number and the number that you are going to do now, right? Counting the number of surjective maps F, let's say, from N to K.
Hello, sir.
Yes.
Sir, should the relation that we are talking about, should it differ by a factor of k factorial, like
Exactly.
something?
Exactly. Right. Exactly. Good. So that means you have arranged this in balls. So last time, let me just write. Good. Last time we have arranged in balls into k identical. Just to remind you, from today onwards, I'll try to post notes, because earlier I was using a software that size was too big. I was not able to upload it in the Moodle, but I'll try to upload the notes from today. Last time we have arranged n balls into k identical boxes such that no box is empty. As two of you pointed out, how do you make it surjective? We distribute this n balls into, let's say, k identical boxes. Then we label the boxes in all possible way, right? That's the reason someone already suggested that the analogy should be factorial k times that Stirling number of the second kind, right? Is that what you said, Nilarjan? I think
Yes,
so.
sir.
Yeah. Okay, so good. So number equal to factorial k SNK. Notice that someone already asked in the last class, so what is this number SNK? So far we have not written any closed form for this number. Unfortunately, this number does not have a nice closed form, but we'll write something as we go on. So let's build slowly. Okay, so this is the number that you want to compute. Okay, so let's do a small exercise as we go on. Let's let x be any integer, positive integer, of course, and then you prove that x power n is equal to k equal to 0 to n snk xk. What is this notation xk? This comes from binomial theorem. Xk is basically x minus 1, x minus k plus 1 up to this product. So which is same as factorial k x choose k, right? Because this is, if you just expand, it is x minus k factorial and k factorial get cancelled. And this top quantity is precisely factorial x by factorial x minus k. Okay, so let's just try to see this exercise. So it's not difficult, right? Can you try it? Someone who has not seen it, I mean, allow others to learn also. Okay, so this is like a, looks like an algebraic identity, right? Something is in left equal to something is in right. So what is the left side count? Yeah, yes, someone said something. Okay, so what is the left hand side? Let's interpret it combinatorial. What is the number x power n? I want to give a mathematical interpretation of LHS and prove the same interpretation from RHS. Instead of doing a brutal calculation proof, we'll do like a logical.
Hello, sir.
Yes.
Sir, if we want to calculate the number of n character strings and we have x
Hmm.
options for each
Hmm.
of them.
Right. That's good. So that is what is LHS, right?
Yes, sir.
LHS equal to what you said. I just write in a slightly more mathematical language. Number of functions. That's what you said, right? Functions
Yes, sir.
from 1 to n to 1 to x. By the way, in mathematics, already probably you know from your algebra classes, this notation is generally used to denote 1 to n. Similarly, you can use this to denote this box notation is a set. Right. So what is the number of functions from 1 to n to 1 to k? That's very easy, right? How do you count that? Because everybody can be mapped in x ways. That's the number of functions. So each of these n element can be mapped to the x ways. So that number is x power n. So this is your LHS. And let's try to interpret the RHS. So remember that when you count the functions, it of course not necessarily to be surjective. In fact, there will be a lot of boxes that will be empty. Okay, so now how do you count the right hand side? It's rather simple. Choose look at the summation over k, right? And this magical number tells you what to do. It is like choosing, you do not know whether some boxes will be empty. So allow that emptiness. Choose k box out of x, distribute the balls into them, and then label these boxes by all possible ways. That is same as counting the numbers, counting the functions. True? So
we can choose any case, I mean k length subsets from the 1 to
that's
x
what I
set.
am doing. Yeah, that's what I am doing.
Okay.
So k boxes means in your language it's subset. Same thing.
Yes, sir.
So choose k boxes. Yeah, sometimes I'm making it more intuitive, so I'm interchangeably using this box, set, all these words, so that it becomes more fun than a tedious writing. Choose k boxes out of out of x and place n balls in them, then label the boxes. That's nice, right? So you choose k boxes out of x, in x choose KOS. Once you have these boxes, you can think of they are like identical at the moment. So you can place that n distinct balls into them in this much way, and then you allow your box to be labeled. Yeah. And as
but
I
all
said,
of them should be non-empty, right?
yes. Why non-empty? Because I am counting the left hand side, I am counting all maps. There could be many things empty.
So, but I mean, among the k chosen,
Yes.
there should be none of them should be empty, right? While we distribute n balls into them.
Yes. So, but this SNK is precisely that number, right? None of the boxes are empty.
Yes.
So this is k equal to 0 to n, and which is same as k equal to 0 to n. SNK. Notice one thing, that this art of combinatorics really lies in answering problems without brutal calculation. We cannot avoid calculation everywhere, but the better combinatorics you learn means you can this kind of bijectively you can argue. That's the methodology that Stanley always follows. Avoid calculation, try to make intuitive proof. Okay, so let's move on. Yeah, so let's maybe see another example. Simple example. Let's try to prove. Yes.
Just a
I
question.
did not understand RHS clearly. Could you repeat?
RHS. Okay. So the LHS is a set of all functions, right? So
Yes,
now
sir.
let's count the set of all functions from the RHS side. So there are n numbers and there are x numbers in this set. So I want to count all the mapping. So how do you count it? Think of these x numbers like x identical boxes. Okay. Among the x boxes, you choose any k boxes. It's not identical, like, I mean, it has numbers. I choose this out of x, I choose that k boxes basically. And then in these boxes, I distribute the numbers such that no box is empty. So what will happen? You will basically split. Maybe you have selected box 1, 2, 5, right? And then this 1 to
Oh,
n,
yes, sir. Yes, sir. I got it. Yes.
got it? And then you can relabel this box because it is the all possible maps. That's why you multiply by k factorial. Yeah. So let's do another example maybe. Let's put 6, SN3, 6, SN2, plus 3, SN1. Let's prove this is equal to 3 power n. Let's try to argue this. So how do you even attack this kind of problem? So one side is obvious, right? The RHS. So what is RHS? Number of functions from what? N to 3, right? True. Let's now argue the left hand side. Somebody wants to try? Particularly who has seen these things for the first time, not already in some camps or some training program earlier. How do you analyze the left hand side? Try. Yes.
So I guess so the first term is like the number of surjective functions from one, like, yes,
Right.
yes.
Right. Exactly.
And the rest are like surjective functions from like 1 to n to a subset of size 2, like.
Exactly.
And
right. That's
third-
it. Your idea is correct. So what is the first thing? Everybody followed what he said? So first thing, it's just like all surjective map. That's what we just discussed, right? Now, since the RHS is all maps, it need not to be surjective. So this term is all surjective. Right? Let's analyze this term. What is this term? You are employing choice, like you will leave out one of the 1 to 3 and take 2. So in 3, choose 2 ways, you pick up maybe these 2. And then you arrange that all the numbers in these 2 places, and then you make it 2 factorial. You label them. And the final one, you choose just only one, you choose, 2 are empty. So 3 choose 1, you choose. Everything should go there. There is nothing to label, and that's it. So these are the possibilities can happen. So left hand side equal to right hand side. Clear? This is simple things. We have not yet started the hard combinatorics so far. This course, we do not have a lot of hard material, all basic stuff. Mixing combinatorics, graph theory, probability, group theory, set theory. We'll just give a background building. Okay, so after this discussion of the Starling number or surjective functions, the next important topic is integer partition. How many ways you can partition a number, basically? For example, if you want, what do I mean by integer partition? So if you want to partition the number 5, so these are the partition. This 5 itself could be a partition, and 4, 1 could be a partition, 3, 2 could be a partition, 3, 1, 1 could be a partition, 2, 2, 1, and 2, 1, 1, 1. How many here? 1, 2, 3, 4, 5, 6, and all 1. That means, so it is a partition of a number. So it does not make sense to take 1, 4 and 4, 1 together. So order does not matter. So you will, once you include 4, 1, you will not include 1, 4. So these are not ordered. So these are like partition so that their sum add up to 5. And it is usually a, usual practice to write any such partition starting with the largest number and in a non-increasing way. There could be repetition, but it should be a non-increasing way. Why I do that? It will be soon clear. Something called Ferrer diagram, but at the moment I am not saying that. So is it clear what is the meaning of partition? Just from the example. So the typical question that people will ask, you will be given a number n, and they will ask how many ways you can partition this number. You can use any number of numbers, right? Any number of partition. Like for example, this is like a 4 partition, this is like a 5 partition, this is like 3 partitions, 1 partition, this is 2 partitions. So any possible way you can partition. That means this example says the P5 equal to 7. 1, 2, 3, 4, 5, 6, 7. There is no other way to partition the number 5. Right? That means intuitively what is happening? Given n, Pn is the number of ways we can distribute n identical balls in identical boxes. There is no bound on the number of boxes. Obviously, it cannot be more than n. In particular, sometimes people can ask pkn. Pk means the same problem where the number of boxes will be limited to k. There are different variants of these problems. So this is of a lot of interest in combinatorics to find these numbers, find Pn, find Pkn, to calculate these numbers. This has a long history. It comes from partition functions in statistical physics. So this has a lot of practical importance also, counting these numbers. So in particular, when you write n as one of the partitions, let's say this, typically means that these are positive integers. So a1 is more than a2 more than a2. And a1 plus a2 ak equal to. This is the meaning of a partition. Is this clear?
Yes, sir.
Okay. So interestingly, although this looks like something really simple, partition plays a very instrumental role even in the higher mathematics. Like when you grow up and study group theory and representation theory, you will see that this partition plays an extremely important role, and lots of this advanced mathematics can be reduced to problem about partitions, particularly when you want to study symmetric groups. Yeah, you have probably already, are you introduced to symmetric groups in any course? Like, is there any algebra course already offered that teaches symmetric group?
Not yet, sir, for BSc first year.
No, first, you have not done any course on algebra so far?
So we have, but not group theory yet. That will be this semester.
So what was the content in algebra 1 roughly? Just I want to know so that there will be some overlap with this course. So I'm just trying to have a feel.
Linear algebra. Maybe.
Linear algebra. Okay. And okay. But then you are introduced with fields and vector spaces, all these things.
Yes. And today only sir started bilinear forms. So yeah.
What? Bilinear forms.
Yes.
And the fields means, I mean, you have introduction to finite fields, or it is mostly you have introduction to rational numbers and
infinite R and C.
R, Q, C, this kind of things you have introduced. Okay. And this semester you are doing group theory, is it?
I haven't started.
Haven't started. Okay. So what is the syllabus roughly in algebra 2? Is a group, ring, and
probably those things will get introduced at the end of the course.
End of the course.
Today sir started bilinear forms. So
who is teaching algebra 2?
Manoj Kumar is.
Manoj is teaching. Okay. Because we will also have some group theory from the angle of combinatorics in this course. Okay, so let me introduce an interesting thing that's called Fourier diagram. This is the main combinatorial tools that you will use when you study symmetric group. Later, not now. In this course also, I plan to teach symmetric group. I will do it sometime. Okay, so what is Fourier diagram? Or every partition you can associate a picture basically. It's very simple picture. Suppose I have taken this partition n equal to a1 plus a2 up to ak, that adds up to n. I can actually draw, and you remember that this is my practice, that a1 greater than equal to a2 up to greater than equal to ak. So the Fourier diagrams is very simple object. So you take a1 many boxes, and below that you draw a2 many boxes. Maybe it will end here, maybe it is equal to a1 also, but it will never cross a1. So this is like a2, and then a3, and so on. So a typical Fourier diagram will look like this. That means this is like a1 blocks, a2 blocks, ak blocks. Apparently, this picture is extremely interesting in combinatorics and in many other places. For example, if you take 7 equal to 4 to 1.
AK should be 1.
No. That whatever you choose, that number. So this is an example just. So 7 is like, you can draw the Fourier diagram for it. 1, 2, 3, 4.
Is it same as the Young tabulus or something?
Yes. It's close to that, yeah. In fact, these things, this is the reason that I said these things will play a role into group theory. So, but yeah, I am not going into that deep at the moment. I'm just doing some basic stuff. Yes, you are right. These things are like Young tabulo. Yeah, all these things can be manufactured from here. For example, this is the picture of the Fourier diagram with the partition 4 to 1. Right? Good. Take, for example, 10 and take this partition 4, 3, 2, 1. So let's draw the Fedor diagram. 1, 2, 3, 4. 1, 2, 3. 1, 2, 1. So now notice one interesting thing of this Fedor diagram for 10, for this particular Fedor diagram. If you count it from the column side also, it is the same thing, right? If you count row side, this is 4, 3, 2, 1. From the column side also, this is 4, 3, 2, 1. Right? And this gives you a definition, self-conjugate.
And this AI should be strictly decreasing, or can both two rows be equal?
Two could be equal, but they are like non-decreasing.
Okay.
Sorry, non-increasing. They could be equal, but non-increasing.
I guess.
So right. If a Fedor diagram gives same partition from, so notice one trivial fact is that this number of total boxes in the Fedor diagram is your number n, right? That's trivial to observe. If a Fedor diagram gives the same partition from row side and column side, we call the diagram self-conjugate. Okay. Right. Any question on the Fedor diagrams? Very simple thing. Okay. So now
Sorry, the
yes.
integer partition which you were talking about before, that is very similar to the n identical and n identical balls to k identical boxes, probably.
Right. It is exactly
Yes.
same. Yeah. That's what I wrote also, I think.
Okay. Like
Yes.
it is a
Number of
summation
ways-
k equal to 1 to n, n minus 1 c k minus 1. Right?
Yeah, that's what I wrote. Like it is the number of way you can distribute an identical balls in identical k boxes.
Okay, sir.
Okay, good. So apparently this Fedor diagram it offers you very nice way to prove a few result in combinatorics. So for example, look at this following lemma. So prove that the number of partitions of n into most k parts is equal to partition n such that no part is larger than k. Okay, so what is the lemma saying? Lemma saying that if you want to write, let's count the number of way of writing the numbers n in the partition in at most k part. That means you are using like a1 to ak, at most k part. It could be less than that, but not more than k, not like k plus 1 and so on. So look at that number. So you can think of like that number is p less than kn, at most k parts. So the lemma asks you to show that that number p less than equal to kn is same as the number of partitions of m such that no part is larger than k. Is the problem is clear?
Yes, sir.
Okay. So now think about this problem. If you, how do you attack such questions? If you want to count it like brutally, you may land up in some trouble. How do you count these numbers and show that they are actually same? That could be very tedious.
We can form a bijection between the two diagrams.
Exactly, good. So we can form the bijection. That is exactly what is the first use of this diagram. So that means if you have a partition of this number into k parts, then you know that there is a diagram, right? This is A1 and this is A2 and the last one is AK. But then you know if you sum it column wise, you are again going to get the same number. But the column wise, you cannot have more than k, right? Sorry, just if you take the strength of the first column plus the strength of the second column and the strength of the last column, none of the column will exceed k. So for every Fairer diagram that satisfies the first property, you can construct bijectively another Fairer diagram that satisfies the second property. Just a minute, I'll just back on it. These two sets are same just from the picture of Fairer diagram. Okay. Okay. So this is nice. So let's observe another lemma, that number of partitions in into distinct odd parts is equal to number of self conjugate partition of n. This is the second problem. Slightly difficult than the first one. What this problem asks? The number of partitions of M into distinct odd parts is equal to number of self-conjugate partition of n. Self-conjugate partition means self-conjugate in the sense of Fairer diagram. If you make that A1, A2, AK, then if you read it from column side or row side, they look same. So this is a problem. The number of partitions of n into distinct odd parts is equal to number of self-conjugate partitions of n. How do you prove it? This kind of thing. Is this color visible? The color I'm using now? Or is it bad?
So it's visible.
It's visible? Okay. Because I'm mixing many colors, but it becomes more attractive. Okay, so let's again try to put a bijection. How do you put a bijection? You start with a Fairer diagram that is self-conjugate. Yeah. And then from there you construct a partition of the number into distinct odd parts and vice versa. So let us consider the self-conjugate I'm not writing figure always. I'm just writing if diagram. Okay. So let's look at the diagram. So let's say n equal to a1 plus a2 plus ak, and this is self conjugate. So this picture gives a lot of ideas. This is a1, a2, and maybe ak. Okay. What I want from this thing, I want to construct a partition of m into distinct odd parts. Okay. So let's see how I can do that. So what I'll do, I'll remove all the boxes from the first row and all the boxes from the first column. How many I have removed?
2a1 minus 1.
Correct. Their number is, as someone said, 2a1 minus 1. After you have removed it, remove from the second row and the second column. How many of will you remove? After you have removed that thing, remove from the second row and second column. Repeat.
So
This
2a2
process.
minus 3.
Correct. Repeat this process for the next rows and columns. Good. So next time when you do this process, what you get is 2a3 minus 1. Right?
So 2a2 minus 3.
Sorry, 2a2 minus 3. Sorry, I missed it. 2a2 minus 3. And repeat this process. So if you repeat this process, so these numbers that you are getting, 2a1 minus 1, 2a2 minus 3, what will be the next number?
2a3 minus
a3 minus
5.
5, probably, yeah. So these numbers you will get. And obviously, you are removing from the same diagram, the boxes, right? So they will add up to n. So they are a partition, and all are odd. And they are all distinct. Why they are distinct? Because you know that from the beginning you have this relation. Right? So they are all distinct now. Clear? That from such a self conjugate tabulo, I have just used the word tabulo, you can construct a partition for n into distinct odd parts. So isn't this nice? Like if you did not know this diagram, then you will think, oh, okay, how shall we set up a bijection? You may get confused. But this picture really makes our lives very simple. And this other part, that from a partition of distinct odd part, you can compute the self-conjugate tabulo. I just leave the other side as an exercise. It's very similar argument. I think all of you can complete it. Just you have to manufacture, I mean, from the distinct thing, you can already say, someone can actually say it. If I give you a distinct partition like that, how do you place that?
And fold by the middle element, like
correct. Yeah. And then you can draw the picture, right? From the picture, yes. You can just write that formally.
Yes, sir.
Okay, so good. So this was my introduction from the basic theory of partitions. Now, one really important thing that we did not do, we did not count the number assembly. So now we are warming up, we'll warm up for that. For that, let me introduce the method of sieving. This is also called method of inclusion and exclusion. Inclusion, exclusion. So what we are doing at the moment, essentially, we are touching different main modules of the combinatorics course, and it's like we are searching in a huge space and giving you some ideas of different main tricks of combinatorics. And finally, we will need, I'm developing some technique, and we will need these techniques to solve maybe harder problem, maybe into graph theory, into probability theory, into group theory. Then you will see that all these methods will come handy at some time. Okay, so let's look at the method of sieving, which is also called method of inclusion and exclusion. So the basic problem is very simple. You have lots of sets, A1, they may be intersecting, A2, A3, these are finite sets. And we just want to count suppose there are n finite sets, A1, A2, An, these are finite sets. Want to count union of AI. This number. Obviously, this is not sum of size of all sets, because some member can appear in multiple sets. So if you just add them, you will have a wrong count. Right? And this method of inclusion, exclusion, or method of sieving offers you a way to count this number. I guess this is also probably known to some of you, but let me just state it as a theorem. You can play with some basic that I'm not doing. I think it will be really boring to do that in the class. You can play with some Venn diagram and get used to what could be a possible theorem statement. But the theorem is this is equal to summation of cardinality of the all sets minus cardinality of the intersection taken two at a time, and then you add three at a time, I1, I2, I3, and then take a minus and take size of the intersection of 4, and this process continue, and last term will be minus 1 power in case it will be n minus 1 intersection of everything. This is the main sieving formula. Is it clear what I have written? Like, is this notation is clear to all of you? If you have any confusion, just this is the time to ask. So here, like, you add all of them, you take 2 at a time and take the intersection, subtract, take 3 at a time, take the intersection, add, take 4 at a time, take the intersection, minus, and this process continues. And depending on n, you end up either with a positive sign or negative sign, and you take the intersection of all of them.
Hello, sir.
Yes.
Sir, the order in which we take the intersection in this intermediate terms, that should not matter, right?
No, that should not matter. There is no order. These are all unordered things. So is that my sequence notation confused you? There is no order. Like, it is like a collection.
Oh, okay, sir.
So how shall I write it? It is maybe, if you are confused, I know. If you are confused, just
so
write.
You can put, I mean, I1 less than I2 less than I3.
That
then
also,
that will
yeah,
be
that also
considered
you
one.
can put, yeah. Several way you can write here. You can write. Right. So there is no order. Is there any other doubt on what I have written?
Sir, could you repeat what you said about order? Sorry, I didn't catch.
There is no order. So
Oh,
what is
yeah,
the first term? Let's interpret it English. Then you can use your favorite notation. No, not a problem. The first term is the sum of the cardinality of the all sets, right? And the second term, you take the collection of all possible pairs and compute their intersection, add them and subtract. So there is no ordering. The way you intersect AI and AJ, you don't count it again into AJ and AI. So you just count it only once.
Yes, no, we just do this for convenience, right? Like we don't want to
Yes,
count
yes,
it.
right. So, yeah, that's right. So in combinatorics, it sometimes our life becomes really boring when we look at this expression. But when you talk it in English or as an expression, it becomes more interesting, more intuitive to say what's going on. And then I collect 3 sets at a time and take their intersection and add. And this process continues. Right. Yeah, probably my notation is not the best, but I hope you understood what I meant. Okay, so let's try to prove it. Actually, this proof is really elementary and it uses nothing more than your 10+2 knowledge. Basically, what is the problem? When you look at the left-hand side, in estimating this union, we should not overcount, we should not undercount. We should precisely count it, the contribution of a number. So let X be a number that appears in T sets, because I said, right, the sets could be intersecting. So I have fixed any number X that appears, let's say, in exactly T sets among these sets A1 to A, right? So what is the contribution of this number in the left-hand side? Left-hand side is simply union. So the contribution of the number is 1, right? You have just contributed the number only once. So the left-hand side, the contribution of X is exactly 1. So we have to only argue that the contribution of X in the right-hand side also 1. And since this X is an arbitrary element, if we prove this for an arbitrary element, we are done. Then no element is overcounted or undercounted. That's the idea, right? So now in the RHS, let us count the contribution of X. Let's count it term by term. So what is the contribution of X in the first term? It appears in the T different sets, right? Then it has counted exactly T times. Ajay, are you saying something?
Yes, sir. I told T.
Okay. Okay. So first thing, as you said, it is T. And then similarly, from the next, look at the next expression. There are T sets that contains the element X. And if you intersect pairwise in any T choose 2 ways, then you will get a contribution for the number X. So the second term is T choose 2. Similarly, the third term is you take 3 at a time, T choose 3, and this process continues, and the process ends at -1 power T minus 1, T choose 2. You have taken all them together. So this is the contribution of X in the right hand side. Is this clear?
Yes, sir.
Okay, so now this is very easy, right? So what is what is this value? This value is 1, right? Why is this value 1? Because of this simple identity that this is equal to 1 minus t choose 1 y plus t choose 2 y squared minus 1 power t choose 3 y power, because of the binomial expression, and then put y equal to 1. So that this side is 0 and this side is 1 minus, so let's call this element, this thing that we want is z. So this is basically 1 minus z, imply the z equal to. So right. So this is a very simple and intuitive proof that to count the exact union of multiple sets, they could be intersecting in any ways. It's enough to compute individually these terms, which are often easier. We'll see some examples, and then just add or subtract them suitably. And the proof is really elementary. It does not use anything more than your 10 plus 2 ideas. But it's a very powerful theorem. This theorem is called method of inclusion exclusion, and for some reason it's also called sieving. Any doubt? Okay, so if there is no doubt, so let's look at a few important examples of the sieving principle. The first example, I think this is probably you have encountered in your 10 plus 2 also, particularly if you have studied a book like, let's say, Hall and Knight or something slightly advanced algebra. But here we'll address this problem by using inclusion exclusion. This problem famously known as hat check problem. Or de-arrangement problem. This problem has several names: hat check problem or de-arrangement problem. So what is the problem? You have n hats or n letters. 1, 2, n, and n envelopes. 1, 2. Goal: want to place the letters in the envelope. I mean, each envelope will contain exactly one letter, okay, such that letter I does not go to envelope I. So if everybody is displaced, that means you want to count the number of ways you want to arrange n letters in n envelopes marked with 1 to n, such that for no I, the ith letter should go to the ith envelope. You want to count this number. How many ways you can do it? And there are multiple ways to think about this problem, but if you think this problem in terms of this sieving method, it becomes particularly simple and elegant. So let's try to answer it. So let AI be the set of arrangements such that letter I goes to envelope I. So that is a bad case for you, right? You don't want it. So number of bad cases. Bad cases means these are the arrangement that you don't want. They have violated your condition. So number of bad cases is union of AI. That is more precisely on. This is the bad cases. These are the bad cases because these are the precisely the cases when some or many are placed in their respective envelope. So that's you don't want that. Okay. So and this is the number that you want to count. If you could count this number properly, then you will be done. Why? Then the number of dearrangement will be what? What is the total number of placement? Since every letter should go only, I mean, every envelope should contain exactly one letter. So the total number of arrangement is n factorial. And this is the bad choice where the condition is violated. And this is your correct number. Is it clear?
Yes, sir.
Okay. So now let's use the method of inclusion exclusion to count this big union. Very simply. So how do you count that? So let's count maybe when you have j many, right? I mean, let's, because we know this is the big sum. So let's count when you are counting the intersection size of j many. What do I mean by that? So when you are counting the intersection of ai1, ai2, aij, that means the letter i1 has gone to the envelope i1. Letter i2 gone to the envelope i2. Letter ij gone to the envelope ij. Others are free. Other can go in any way you can go. You can choose them. So what is this number? So these envelopes are fixed and others have freedom. Yes. So this is exactly. Milan, did you say anything?
No, sir. We should first select the J envelopes, the J boxes out of the. And
this is even very simple, right?
Oh.
These boxes are fixed because the definition of AI1 means these are the arrangements where letter I1 is going to the box or envelope I1. So this is already marked, see in the picture. Now, what are the letters?
So we can just defer the rest of them. I mean, in n minus
exactly.
factorial.
Exactly. So this is n minus j factor. Right? Good. So now we have the nice formula in hand, that union of this AI.
So
yes.
So in this n minus j factorial, what if some other letter also pairs with the correct envelope?
What is the other letter? That does not matter. That's precisely the point of inclusion exclusion.
So won't that become part of this intersection?
Which intersection?
If, for example, ij plus 5 goes to envelope ij plus 5.
Yes.
Then the whole number will become.
Yes, that does not matter. As long
actually.
as these things satisfied, but that is the whole point of inclusion exclusion, that you are not thinking this mix up. So this mix up is taken care by that big formula.
By the exclusion of the next one.
Yeah, that's the beauty of this method. Yeah, good point. So, right. So now let us go back and see the expression that we wrote. Yeah, so this is the expression, right? So I'll just write this expression in a more compact way. Okay. So this is like j equal. I'm not doing anything. I'm just writing it in a slightly more compact way so that it will be easier for me to write. And this number. Don't get afraid by what I'm writing. I'm writing the same thing in a more mathematically precise way. J and I. So I just wrote this huge summation in a more compact way. Like this is 2 at a time, 3 at a time, and the sign is, if 2 at a time, sign is -1 power 2 minus 1. Here sign is -1 power 3 minus 1. That's positive. The same thing I have written here, j at a time, -1 power j minus 1, and this is like all j at a time thing. For one such thing, I computed this cardinality, and these cardinalities are all same. So this number for my case is j equal to 1 to n -1 power j minus 1, and what someone just says, n minus j factorial. Sorry, and then I have to choose all possible j, right? So this is n choose j ways. Which j? I have to choose a collection of j's, right? So this is the bad number that I have. So my number of d arrangements is n factorial minus this number. N minus j factorial will get cancelled, so it will be n factorial by j factorial. Now, since I have a -1 here, I will make it plus, and how do I erase it? Sorry. Make this one disappear. So that is j running from 0 to n -1 power j n factorial by j. But the basic idea remains that essentially your success depends on how the way you define those sets AI. Once you define the sets AI, you can just mechanically compute and solve many problems using this inclusion exclusion. The trick lies in defining the sets AI. This is a very famous example, appears many places in combinatorics. And this is called hat check problems. Okay. So the remaining the time we have today, so let's count the number of surjective functions.
So could you scroll up a bit?
Yes, sure.
Oh yeah, sir, that's it.
Yeah.
Okay.
Feel free to stop me anytime. Yeah.
Yes, sir. Thank you.
Okay, no problem. So now let's go back to our thing that we did not do, the number of surjective maps. Yeah. This is surjective maps from n to k. But one thing we realized that the surjective maps, their number is k factorial snk. Now we can count it very easily. Count in the sense that you can derive a meaningful expression for this object using the method of inclusion exclusion. How shall we do it? Can somebody try? I'll give you a hint, and maybe because it's similar calculation, I will not do the complete calculation. I'll leave it as an exercise.
So total number of functions minus injective functions.
Let's yeah, your approach is right, but let's go step by step. The beauty of inclusion exclusion lies in defining the sets. Okay. So let's go step by step. So let's think like, what are my AIs? So what is my A1, for example? Let's say. Your idea is correct. Like I know the number of total functions. I want to delete from that number the number of functions which are not surjective, right? That means you have to define the sets AI in such a way that that big union for you, for which you have a hammer in your hand, inclusion exclusion principle, will allow you to compute that value. So what is your A1?
Does not use one.
Correct. So A1, precisely the number of functions, the set of functions rather, the set of maps which does not have one in its image, right? These are not surjective. It is not surjective because somebody is missing from the image. So the bad set is AI I equal to 1 to k. Why this is bad? Because this is precisely the set of maps for which somebody is missing. It is not surjective, these maps. And you want to count this number. Now it should be very easy, right? Counting this number. So what is the general term will look like? You can do it offline, but maybe you can just tell me what is the general term look like. General term means these are, again, the general term means I mean this formula, like this, forget about this sign, but there are like you take L at a time and intersect, right? This is what I mean by a general term. So you have to think about what is the value of a general term here and then just do the manipulation. A general term means what? Suppose you want to compute the cardinality of A1, A2, let's say AN. This is like a general term of length L, right?
So if it does not have L of them in its image,
exactly,
and
right?
then
So
the rest
very
n
good.
minus L of.
Very good. So this is like 1 to n, and this is 1 to L, L plus 1 to k. So these things are not used. So everybody is mapped here. These things are empty. So that means here you have n element and you have k minus L elements here. So the number of choice is what? N element is going into k minus L selection. So this is k minus L power n. And then you have to take again this n choose L, the typical trick that I showed in the last calculation. So if you employ the same thing, I think you will be easily able to complete it. So please complete it. So I'll leave it as an exercise. Yeah, I think I will not do more today.
Recording stopped.
Sir, a small question.
Yes.
So do we consider summations to be closed forms as well?
Summation to be?
A closed form.
For this problem, you mean?
Sir, yes, sir. Why I was asking is because if we take this summation that we get and divide it by k,
that is not. Oh, I understand the question. That is not closed form, but it is better than not knowing anything. I mean, that is not what usually a closed form means in combinatorics. Closed form means a closed number, like maybe n factorial by k factorial. It's a number.
Right.
Here still you have an expression. Yeah, good point. Yeah. It's not a close. In fact, there are many things in combinatorics where closed forms are still not known even after 100 years. We only know it's like a expression. Like for example, the partition function, you will, when I'll do generating function, you will see that you know some asymptotic behavior of the function, but we do not know an exact number in some cases. There are many interesting things that still people are trying to find out.
Right, got it, sir. Thank you, sir.
Thank you. Yeah, if you don't have any question, we will leave.
Thank you, sir.
Thank you.
Mm.